Okay, so this will be our first video of the year. Basically, I'm going to pick something important from the unit, something I think that's a key idea or something that I think is difficult, and we'll discuss it in some way. So here, I've picked a problem. I think it's a good one. It's a little bit odd, but it's a good problem. And basically we have two astronauts that are throwing fruit to one another. So one guy's throwing an apple to his friend, the other guy's throwing an orange the other way. I've attached the problem itself, print it off so that you have it handy, and try this yourself before I just show you how to do it, because you'll learn it a lot better if you actually attempt this yourself and then you take a look at maybe places you made mistakes when I go through it. So try it and then watch the video and see exactly how you're supposed to do it. Okay? So now I'm going to start with how to solve this thing. We've got these two pieces of fruit coming towards each other. We need to set up our problem. Normally you draw a diagram, but you're given the diagram. You'd want to pull out important information and ask yourself, what am I looking to find here? Well, the question's actually looking for the apple's direction and speed after the collision. So you guys can see the picture there. We need the speed and direction of the apple, which is basically the velocity of the apple after this collision. What are we going to do to set this up? Well, originally they're coming towards each other straight on, so it's linear originally. It's going to be a bit of a glancing collision. So they hit, and then afterwards they veer off. Now, this should immediately set off warning bells for you. You see angles there. This is a 2D momentum question. That's a really important place to start. It's 2D momentum. So we're going to be dealing with components. All right, that's one thing we know. We're going to be dealing with some trig. We need our calculator in degree mode. Again, the main concept for the entire unit, physics principles, conservation of momentum. Whatever the momentum was of the apple and the orange before collision, that has to be the momentum of the system after. And that's where we got to be careful. The momentum of each object may change, but the total momentum of the system before will be equal to the total momentum of the system afterwards. So in this case, as I said, it's components. So what we're going to do is, you'll see me do this, we're going to find the momentum components before, and those, so the momentum, say, in the x direction will be equal to the momentum in the x direction after, the momentum in the y direction before will be equal to the momentum in the y direction after, okay? Now, something that I'm going to set up here right off the bat, my directions, I'm going to make left and down negative, so anywhere you see left or down, it's going to have a little negative sign on there. The other thing is, never work in velocity vectors, because velocity is not conserved, momentum is conserved. So what we need to do, even though we want to find velocity, we need to work in momentum, and then on the last step of the question we'll convert back into velocity. So what I have up here, I'm setting up my momentum before. So here's all my information about before. Now before, it's all in the x direction, so my momentum in the y direction is 0. I've got it all organized. My momentum in the x direction is partly the apple and partly the orange. I'm given the mass and the velocity of the apple, and I'm given the mass and velocity of the orange. So here's my momentum in the x direction before. Now what I know is, by conservation of momentum, momentum before must equal momentum after. So what's my momentum after collision? My sum of the momentum in the x direction after collision is this. And after collision, the sum of the momentum in the y direction is 0. Obviously, it gets split up a little bit differently, but we know that these are our momentums after. All right, so beforehand, my calculations were simple. Everything was linear. It was easy. I said that my momentum before equals everything after, so I'm taking that information before, and I know it still applies after. It's just things have been rearranged a bit. I have angles, so I need to start breaking everything into components. So to start with, up here, I have my two diagrams. This diagram is a vector diagram for the resultant momentum of the apple, and I've broken it into two components. This is the x component of the momentum of the apple. This is the y component of the apple's momentum. The orange, well, the apple was moving up and to the right. The orange is moving down to the left. I actually calculated the resultant value for the orange's, well, this is actually only the magnitude of the orange's momentum. I calculated that here. This would be the y component of the orange's momentum, and that's the x component of the orange's momentum. Okay? Now these diagrams are key. You really need to draw the diagrams to keep everything straight, because there's a lot of information to organize. So from these diagrams, what I can do, I know that the y component of the apple plus the y component of the orange has to be 0 because the momentum in total after has to be 0. I know that the momentum of the apple in the x direction plus the momentum of the orange in the x direction together have to be this number, which we found to be the momentum of the x direction after. So these are my calculations from the diagram. I know that I've got a total of y in the y of 0 for the apple and the orange. Now, I don't know the apple's y component, so I've just left that. That's what I want to find. But I do know the orange. And I've made it negative because it's down. That's key. So I've got a negative there. It's sign because it's the y component. You got to be careful with that. I won't go over that specifically in the video, but you need to know how to set up, find a y component using the trig. So from this calculation here, this is the y component of the momentum for the apple. And down here, I'm calculating the x component of the apple's momentum. And what's very important about this is I've just got all the information I need now to find the resultant momentum of the apple, because that's just going to be the x component and the y component together. So if I put those two things together, I get my resultant momentum. All right, now I know these are they're long questions. That's why being neat and organized is very important. But what I finally came to, I pieced this together. I'm going to stop for a second and ask myself, is this reasonable? These should be small values because it's an apple and an orange. They don't have big momentums. Good, those are small. Another thing, checking these, this one was positive and this one was positive, which makes sense, right? The apple is going up to the right, so it's going in the positive x direction and the positive y direction. Both of these should be positive numbers. It's a nice check that, okay, they're probably right. When I go through here, this is my final, kind of getting into my final step. What I'm doing here is, I know that these are the two components of the apple's momentum. So I basically got a right triangle. And I'm going to draw a quick diagram here to show you what I mean. Well, actually, I don't need to draw a diagram. I already did. Here's px apple. We found this one, right? So the resultant momentum of the apple is just the third side of a right triangle. So we're going to square each component. And if you go through and you do the Pythagoras' theorem for this, you find that the magnitude of the apple's momentum is this number here. Okay? We're almost done. We need a direction on this. Okay? The other thing is, technically it didn't ask for the momentum. So first, let's just find the direction. The direction, well, it's this angle inside here. It's opposite over adjacent. So to find that angle in there, you're going to just say that tan theta is opposite over adjacent. The opposite is the y component, which was the 0.12419. Opposite over adjacent, the adjacent is 0.088627. And you're going to find that ratio, obviously use second tan to get the angle out. You will find that this angle is approximately 55 degrees. I'm rounding it to the nearest degree. Okay, so now, great, we have a direction which, yeah, momentum is a vector quantity. It needs a direction. So last step here, we've got that, remember, momentum is the product of the mass and the velocity. So to get this momentum into a velocity, we just need to divide by the mass of the apple, which was 0.130 kilograms. If you do that, you get that the velocity of the apple is 1.17 meters per second. And if we want to be technical, the direction is 55 degrees. Just be careful. We've talked about setting up your degrees. Know that, all right, if we're not doing north, south, east, west, if we're not using navigator coordinates, it's always measured from the positive x-axis. So yes, that is right. In Cartesian coordinates, that is just 55 degrees. Just remember that if it's down here, you always got to go from the positive x direction around. Okay? So through this long process, we've been able to find the resultant momentum of the apple. From that, we got the velocity of the apple.